Alrighty, let's slowly get started. So second talk of today will be Zico Kolter. Zico has worked on pretty much all parts of the deep learning pipeline, anywhere from architectures, improved algorithms, robustness, adversarial examples, generalization. On top of all of the best paper and test of time awards and everything else, he somehow manages to find the time to be the newly appointed head of the machine learning department and on the board of directors of OpenAI. I'm convinced he doesn't sleep, even though he says otherwise, but anyways, Zico, please take it away.
Thanks very much, Andre. All right, it is great to be here. I actually so if you check the schedule today for the talks, you notice my talk title is TBD. I apologize, Matthias, I did never send actually a title, but it actually worked out really well for the best for me because I decided on the Uber ride here I was going to change which of the talks I was going to give. So I decided to give a different talk today. I think given the theme, I was going to talk about adversarial robustness, which I give a lot of talks on. Those are all online though, so you can just watch them if you wanted to. I want to talk about instead, I think some work that ties in a little bit better with the themes of this particular set of workshops, which is about hallucinations in generative AI. And I'll define what I mean by that. I'll also try to stay out of the way a little bit from this. I like to walk around as I talk. I want to start off by saying, though, that this talk is essentially exploratory. It's very new work. I've given this talk one time before, and this is the second time. And it's also more trying to demonstrate or show some kind of behavior that I think deserves a bit more study rather than really explain anything in detail. So it's going to be very light on math, very heavy on pictures and sort of plots and such. But hopefully we'll get at some interesting effects that we see kind of in modern generative AI. I also, but you probably can tell by the title that I use the word generative AI here rather than machine learning or statistics or something like this. That's intentional. I'm, as those who know me, I maybe 3 years ago I would have been more well suited to this particular seminar series, but now I'm a scaling maximalist when it comes to AI, so I'm gone to the dark side. But the goal here, to a certain extent, is that I do want to try to make some connections between these two worlds, and hopefully argue that some of the problems that we see in what I will broadly call kind of modern, generative AI are actually due to, in some cases, rather simple estimation errors. And people sort of more familiar with these topics have actually a lot to contribute to them. And that's really the purpose of this talk. Please do ask questions. I do not think I have 75 minutes worth of content, though I can certainly talk that long if people want me to. But I'd rather have questions and have some interaction. So to start off with, this is work really with a master's student, Samuk, one of my PhD students, Pratyush, as well as there's a second section that I might or may not get to, very brief, from one of my students, Andy, and many other collaborators as well, but these are at least the students that have worked on it. All right, so let's jump in, and I want to talk about why hallucinations are so interesting. So again, I'm talking about generative AI here, basically meaning LLMs and diffusion models. So ChatGPT or DALL-E, Stable Diffusion, things like this. And if you've spent any time with these systems, you know that they basically just make stuff up a lot, right? They just say things that are false. In fact, I think there's a great quote that sort of summarizes this, because they're generative models. They don't really have facts or knowledge bases of the world. And so it's actually very reasonable to say that all AI generations are hallucinations. Some just happen to be true. I don't know how she said this quote, so I asked AI. And of course, like all famous quotes, someday this will be attributed to Einstein. But I want to dive into some of these a little bit and sort of show you the nature and characteristic of these things and why I think it's a really interesting topic. So here is, and I should mention, these examples are from older models. So more recent models, hallucinations are a massive problem in the practical use of AI. And I'll mention this again in a second. the fact that these models just say things that are wrong, you've probably all heard in the news, right, where people use them for legal cases and stuff, and there are fake legal cases it imagines, and you can't do that as a lawyer, right? But I want to show some examples of hallucinations that these models do, and kind of also give you a sense of why they might make these errors. So again, these are from older models. So because there's such a problem, a lot of systems have really tried to put in place mechanisms to prevent this. On top of just the raw-based models themselves, they have other sort of checks for these things because there's such a problem. And so the situation is improved a lot, but I would actually argue from a modeling and sort of basic technology standpoint, the problem is very much still there. So a year or so ago, I asked ChatGPT, as you do, to write a biography of yourself. So I asked it to write a biography of me. I am a good example for this particular failure mode because I am on the internet. I have a web page. Obviously, my web page was scraped by these models when they were sort of building themselves. But I don't have a Wikipedia page, so there's no sort of ground truth knowledge about my sort of biographical details that are out there. And so what it says is that Zico Kolter is a prominent computer scientist, a machine learning researcher. That's true, right? 1 for 1 so far. He was born in Brazil in 1986 and grew up in Rio de Janeiro. That is not true. That is entirely false. But you wouldn't know that unless you didn't know me, right? No. Bachelor's degree from the Federal University of Rio de Janeiro in 2007, also not true. And PhD in computer science from Carnegie Mellon, also not true, though it's getting more correct, right? Maybe a little bit closer. And then it says, I'm on the faculty of School of Computer Science. That's true. So 2 for 5 or so now. And I'm a co-founder of a startup, Acon, also made up and does not exist as a startup. I assume most people sort of are familiar with the basic idea of how LLMs work. They predict one word at a time. They predict sort of the most likely words and sample from that distribution. The reason why it does this, why these things come out, is that for those that maybe have not heard of these people, I was named after a Brazilian soccer player, actually, a football player, who was big during the '82 World Cup. And so if your name is Zico, the most likely year you were born is around 1983 to 1986. And most likely you were born in Brazil. And then if you were born in Brazil and you're an academic, you probably went to the University of Rio de Janeiro. And then it starts, again, going back to sort of facts it has. So maybe I got my PhD, I probably got it from Carnegie Mellon, stuff like that. So it makes total sense why it's doing this. Again, just happens to be wrong. Here's another example I really like. This is a meme that's been going around for a while. AI is known to be threatening to replace a whole lot of domains. And of course, people say, AI will replace photographers, and then AI accepting the job has a whole bunch of hands shaking themselves that have more fingers than are normally common on hands, or different configurations of hands and arms than are common in the world. And I mean, these are awesome. And I think actually, in some sense, sort of artistically, hallucinations make for the best examples of AI art in a lot of ways. But I think that there is really sort of a fundamental connection here to what I'll broadly call generalization, but I'm actually not going to use that word too much here. I think when it comes to LLMs, what it means to generalize is honestly not as clear as in other settings. But speaking at a very high level, I think it's fair to say that if we expect these models to generate anything outside their training data, then in some sense, it might be reasonable to expect that they kind of have to place some probability mass on statements that are not true, right? These systems are not, they don't have a model of the world underneath them. They don't have sort of detailed conceptions of what's true and false in some knowledge base. They're just statistical machines on some level. I mean, to be clear, I think they're also intelligent. I do believe that. It's one of the most amazing scientific discoveries is the fact that if you take these statistical machines and iterate them, you get intelligent responses out. That's incredible. But it does seem to a certain extent that, yes, if you are generating text that goes in any way beyond what you have seen before, you have to have some mass on things that are not true. So maybe hallucinations are just a fact of life when it comes to AI models. At the same time, though, I think it's also fair to say that this is the single biggest obstacle we have to a more widespread adoption of generative AI, right? Because you can't use it for legal applications, arguably, if it's going to make up case names and things like this, right? Natty's wondering about this. Well, to be clear, I use generative AI all the time for everything I do. Coding and such, right, is the one thing I use it for most. So yes, you could argue that this is surmountable, but I do think that we don't want these things. We would like to minimize this as much as possible. Okay, maybe a more fair statement. Okay. Yeah, absolutely. Humans make mistakes on hallucinate all the time. Somehow, I think these are of different character, though. There is a way in which we have a bit more recourse, I would argue, to sort of facts in the world and things like this than some of these models. But maybe that's just a matter of their deployment. To be clear, as I said at the beginning, I am a scaling maximalist. I believe that these things are going to ultimately reach the heights that we are thinking they might right now. But I think this is still a practical problem. So what I want to, and to a certain extent, of course, this is a problem. Of course, all these generative models, they're going to, I mean, this is true. They're going to put probability mass on things that are not true because they don't have a model of the world. They don't have sort of fact databases in some sense. But what I want to try to argue today and give some hints of, and in a very informal way, and really I hope to actually just provide kind of a background that would lay a foundation for more work by this audience or others, is what I want to convey is that this is not the only cause for hallucinations in generative AI models. And in particular, what I mean by that is that there are many cases where, to a certain extent, and I'm anthropomorphizing here a bit, but generative models, in some cases, some of the hallucinations we see are not unavoidable in the sense that I sort of mentioned before. They are actually cases where the model very much knows that it's hallucinating. Or in other words, there are statistical differences between the generation of hallucinations and the generation of factual responses, or good images with many fingers and images with the correct number of fingers on a hand. These are, in many cases, things that the models actually do know. And the generation of hallucinations is a sampling artifact. It's about how we sample from these things, given their model of the world, and not an inherent problem of the models themselves. And I don't think all hallucinations are in this category, but I think that some are. And that's what I want to try to argue today. Okay, so with that as the background, the outline of this talk is going to be the following. I'm going to talk first, and to be honest, I might spend possibly all the time on this first one. This next one is very brief, and it's more just sort of an informal exposition. I want to spend some more time talking about the first one, which is understanding hallucinations in diffusion models using a phenomenon that we call via a phenomenon we call mode interpolation. I'm then going to talk about, if there's time, maybe a little bit about identifying and mitigating hallucinations in LLMs. And I'll end kind of reiterating my sales pitch about the value of investigating these phenomena from a more statistical perspective at the end. All right, any questions before I jump right in? Okay, please do interrupt and ask questions during it. It will go very fast if we don't have any questions, so I'm sure there will be. All right, this paper, and it's really the main thing I'm going to talk about. This is about from a recent paper we have called Understanding Hallucinations in Diffusion Models Through Mode Interpolation. That's very similar to my title there. This was posted. We posted this on arXiv a couple months ago. All right, so first of all, I want to define hallucinations, and I'm going to use a very informal definition here, but it's just sort of hopefully clear what I mean by this. If P is our distribution of the real data, and Q is some distribution that we sample from to generate samples. Again, when your data are things like all images that there are, I know it's impossible to actually characterize these distributions. I'm not going to really try to talk about this in any meaningful way, I would argue. But I do want to have some sort of notion of these things here so we can define what we mean by hallucinations. I would look to everyone else, if they're interested in this, to sort of start formalizing this more. But basically, a hallucination, to be blunt, is any point sampled from our sort of data generating distribution Q that is not in support of P. So it's something that would never occur in P. And I do really want to use the word zero there. It should be something that would never actually occur. You could also replace that with the probability being less or the density being less than some infinitesimally small quantity, less than the atoms in the universe or something like that. But let's just go with this for now. This will never happen in real images. Whatever the distribution of real images means, I'm sweeping that all under the rug here. I'm being very informal. And what the key question I'm going to ask is, what is the nature of this set of points? What is the nature of points that, in this case, diffusion models typically hallucinate about? And to sort of motivate this, I'm going to use some simple examples here that we've constructed when we started investigating this phenomenon. And the first data set I'm going to use to motivate hallucinations and later sort of to analyze some of our hopeful understanding of this is a data set that we call the simple shapes data set. And what this is a data set of black and white images with shapes. The shapes are triangles, squares, and pentagons. And they're always in this configuration. They're never rotated or anything. It's just this kind of triangle, a square, and this pentagon. And in particular, the triangles always occur at most 0 or 1 triangles occur in this region of the image. 0 or 1 squares occur in this region of the image. And 0 or 1 pentagons occur in this region of the image. So, right, so they could be anywhere in those regions, anywhere there. And they will either occur or they won't. There's only ever 0 or 1. This is a well-defined distribution now. It's actually discrete because images are discrete, but this is a well-defined distribution. We can exactly talk about support of things, of possible points. And we can talk about points that are imaginary in some sense. So if we take data from this and take them on the order of tens of thousands of examples here and train a diffusion model. I will talk in a second about what diffusion models are. I'll do it very briefly because hopefully most people are at least roughly familiar with diffusion models. These are the models behind things like DALL-E and Stable Diffusion, and Flux is the latest one. They're models that generate images essentially by creating a distribution of samples that interpolate between the image and noise, and then trying to essentially predict the image from noise, as meaningless as that might sound. They sort of define a distribution in a way that you can at least generate images from these initial noise distributions. Okay, so you take images like this and you train an off-the-shelf diffusion model. And for the most part, you get images that actually fit this, that are exactly from this distribution. So we have a model that is sufficient to exactly capture this kind of stuff. And then they capture crisp images and things like that. The images look correct. They're all good. But occasionally, you get something weird. So even if I'm just giving it data like this, occasionally, you get points that have two shapes in the same region. They're usually in the correct region, but they're just two sometimes. It's kind of weird. You've never seen that in your data set before. I mean, you could argue, this is a big distribution. So there's a lot of things you haven't seen in your data set before. But this is a very particular failure mode that they have. They synthesize two shapes sometimes. That's what we see. It's a small portion. It's on the order of 1 to 2% or so. But there's a notable percentage of sampled images that have two shapes. Yeah?
Does the percentage go down if you increase the sample?
Yes, if you increase more and more and more, it will go down, but it will never go away. There will always be some.
Then you could argue it just doesn't know if the training set has very rarely two shapes or like.
That's very true. Yeah. So I mean, right. So with high dimensional, these are all images now, right? So how do you know this? But what I will say is that this seems to be. It doesn't make many other mistakes. It doesn't make circles ever. It doesn't make squares that are rotated. It, for the most part, does things exactly right. Just sometimes there are two shapes. And to be clear, I don't think I'm going to resolve this question about why this is the error it makes. These operate in sort of representational space that's very inscrutable to us. But I think it's very interesting that this happens, and this happens quite repeatedly. This is the mistake that they make.
Do you know if this is a diffusion model specific thing, or do these GANs like to do similar things?
We didn't train GANs in this particular example. I am going to talk just about diffusion models because, in fact, the failure mode I will talk about is specific to diffusion models. So let's just focus on diffusion models for now. I suspect actually GAN stuff would have different failure modes, most likely. Yeah.
Your implicit claim is that this is always going to happen no matter the size of the training set.
It does seem to happen a lot from the, and I will argue why, given, okay, so you could argue that in the limit of truly infinite data, you will get better, but I think this is a matter of the representations of our functions that we use to approximate these things that will cause them. So I suspect even with effectively infinite data, this would stick around. Yeah, this would still happen.
As you said, everything here is discrete.
Yeah.
You need infinite data.
Right.
You could try for a smaller example, smaller dimension.
Yeah.
Giving it every configuration.
Let's talk about that because I'm going to go with a smaller example in a second, and I'll talk about why I think this is still going to be present even with every configuration possible. Yeah.
Does the sum of shapes goes beyond 3?
No, it's always at most 3 because there's only one. Oh, I think likely it does. I actually haven't checked that. Let's take the famous example of hands too. If you take a data set of just hands, of human hands, there are hands that have not 5 fingers, of course, but in this data set, this particular data set of 11K hands, every hand has 5 fingers. And what you get if you train a diffusion model on this data set is you get mostly hands with 5 fingers, and occasionally hands with more than 5 fingers or less than 5 fingers. So thumbs coming out of the side of the hands and things like this. This is also, I don't even know how to think about this because you could argue that this is in the distribution. There are hands with more than 5 fingers, but they're never in this data set. So what's the real distribution, right? This gets into a very fundamental issue of sort of what do we mean about distribution when it's of an object like a hand that we think about as being a physical object in the world, but which we can never characterize all possible images of hands. But having said that all, this is a very sort of immediate problem and a very present problem in that a very high fraction of images relative to what's sort of been seen in training data, and this holds true also for images generated by larger diffusion models, have incorrect numbers or a non-5 number of fingers in their data. Yeah, you will that sometimes too. So sometimes you'll have 3 fingers also, yeah. More is somehow more common. It's much more common to have more than 5 fingers than less than 5 fingers.
Are you arguing this is specifically because of the diffusion architecture, or because it seems like very unnatural?
Yeah. So what I'm going to argue is that this effect is at least partially explained by the diffusion model. I don't think that's the only cause, because I think with this problem in particular, the hands with more fingers, that one you see in all generative models. But what I will say is, I think there is I don't know the mechanism behind all these things, nor do I think we can even, this is why my first title was understanding a bit about hallucinations. I will offer you a mechanism that I think is at least partially the cause for this in diffusion models, that I think there is some hint that it might actually be behind, not all of these, but some of them. And so how general this is, we don't know. How generic this is, rather, we don't really know. Yeah.
So you said that the models mostly know when they hallucinate.
Yeah.
I think that's true for Gen AI, but does that still hold here?
Yes. So I will argue with you that models know that these are hallucinations. Yeah. And I'll say what I mean by that in a second. All right. So before though, so these are the motivating examples. We will come back to these examples, by the way, because in some sense, what really matters in this context is not sort of how well we can, or what will matter here is not how well diffusion models model the toy settings I'm about to describe, but how well they actually model these kind of things. This is what people apply diffusion models to. So I will come back to these later. But before we come back to them, let me give an even simpler example of just a mixture of 3 Gaussians. So let's instead take data like this. So this is a mixture of 3 Gaussians, and we're sampling from 3 Gaussians with identical means and identical variances with mean values 1, 2, 3. If you train a diffusion model on this, what would you expect to see? What do you think it's going to look like? Any guesses? I thought it would look like, I thought it would ignore one of the modes, is what I thought originally. Any guesses of that? Obviously, it's wrong because I wouldn't be asking otherwise. But what was that, Natty? Did I say more?
No,
What?
I said if there are more modes, it'll ignore some of them.
I see. Yeah. So maybe right. So maybe it'll ignore some of the modes. Yeah. If there's 25 modes, we'll have that slide in a second. Actually. Yeah. Maybe. Yeah. I'll reveal it. So we train an off-the-shelf diffusion model on this, and you get data like this. So it puts probability mass in between modes for no obvious reason. Yes?
Isn't it semi-obvious?
Why?
The way it's pushed forward is constructed. I mean, it's hard to really zero out between them.
I wouldn't. I don't think it's actually hard. I think it's for a very specific reason. Maybe it's obvious to you. It was not obvious to me this would happen. Maybe I'll show the next slide. The next slide makes it even less obvious to me what's happening here. But yeah, we'll talk about it in a second. Yeah.
Like the original distribution looks like it's truncated Gaussian.
It's not. This is actually from actual samples. This is a log density too, right? So this is the log density. So it's actually quadratics on the space. What I'm plotting here is the actual histogram of data points. There is a density here, but it's less the number of atoms in the universe at the lowest point. It's not, the fraction should not be 10 to the -5 there that you see. This is a huge overestimate of the actual density there. Okay, so let me show another example because I think it is maybe more instructive about why I think this is weird, not just, oh, obviously this is what diffusion models would do.
Yeah, it's sound dismissive. But for this one, I also expect to put a lot of mass.
Yeah, okay. That's maybe correct here. I think this example is actually more interesting. But even though I'm going to mainly explain it through the three Gaussians. So now let's talk about a 2D grid of Gaussians, of 25 Gaussians. And I also thought it would drop some of the modes. I thought that would be the most likely outcome. If you train a diffusion model on this, what you get is samples that look like this. So what it's doing is it's taking nearby modes, really the nearby neighbors of modes, oddly not diagonal neighbors. So it's in some sense like just the nearest modes in some space, in some definition of a metric, and connecting them with some positive probability mass between the two. Yeah.
I mean, people did this with GANs like a while back as well. It's just because, as Matu said, if you have like a push forward of a Gaussian, to really separate them, you get an extremely non-Lipschitz map, and then it's just hard.
So, but a GAN does it differently. So this happens differently in a GAN, this example. And the reason why this example happens differently is that in GANs, you actually do get some probability mass in these centers here. It's not so well aligned with these things. I don't disagree that it is about the Lipschitzness of the function. We're going to talk exactly about what's happening here and why that's exactly the cause of it. But you get different effects with GANs than just these. Some of it's similar, but it's not identical to this.
How much does it depend on what architecture you put into either the diffusion model or like a...
So I think it does. So this, I mean, to be clear, this is 2D. So this is just an MLP that we're using here. What we use in the actual for the shapes examples, as those are all units. And I think it doesn't really depend there. Now, obviously, what happens there is more complex because what it means to sort of interpolate between modes is very different. But I think I'm going to argue why I think this is actually a similar effect. Yeah.
So when you say unit, you mean like a modern unit with attention is included?
So oh, I'm sorry. Yeah, yes. So Matu said when I'm talking about the other models that I'm using for the other examples, I said that we use a UNet architecture to do the diffusion there. And yes, it's a modern UNet. This is off the shelf, one of the DDPM or ADM models that we use. So it's sort of a standard UNet for that. Yeah, everything's standard. There was one more question I saw over there, but yeah, sure.
So I guess the number of parameters, the actual number of parameters that you need to learn the actual distribution is lower than the other one, right? Because you just need to learn the, I don't know, mean and averages of Gaussians over there.
Oh yeah. So I mean, as with all deep networks, we are wildly over parameterizing our generative distribution. I mean, but it still works, right? Yes, of course, you can fit a mixture of Gaussians to this, and it'll work fine. You'll fit it exactly. You can't fit images that way, right? So people, these methods, for better or worse, are the method of choice for fitting real high-dimensional distributions. And so I think it's quite instructive to look at them, even in this low-dimensional case, because what they're doing here, I think, is somewhat interesting. Yeah.
So if you were to just increase the number of denoising steps to allow for sort of greater non-linearity,
Yeah.
does that just fix this?
No, it doesn't. So it's not about the denoising itself. It's about the underlying representations, which I'll talk about in a second. So no matter how many diffusion steps you use, you'll still get this. So this is independent of the number of diffusion steps you use. Yeah. All right. So the phenomenon that we're trying to claim is sort of behind this here. And this has been seen in other models as well, to a certain extent. But I think it does appear more prevalent, I would say, in diffusion models than I've seen in other models. Is this what we're calling mode interpolation? So the idea is it does appear that most of the hallucinated mass, to use it for lack of a better term here, lies in this interesting set where Z is a point in Q that's not in support of P. This tends to happen in regions where there are 2 points. There would be 2 points that are, in fact, in the support of P. These are, in fact, 2 sort of points that are neighboring in their modes. And then Z ends up being a convex combination between the 2 of these. It seems like most of the mass that we see that's hallucinated falls into that category. Now, the question is sort of that we have is why? Why is this happening in a particular case of diffusion models? And why does it not depend on things like the number of sampling steps you use, the number of Langevin steps you use in creating your sampler and things like this? I think there's actually a pretty straightforward reason, at least in the Gaussian case, why this is happening here, just like this. But I'm going to try to explain that now. Yeah. Yeah. Yeah, so we have some other examples of this too in the paper. Yes, as you move modes further apart, you get less points between them. And it falls off pretty quickly, which is why you don't see points that are sort of in these stuff, in the intervening points there. But it's also, I mean, it's actually very hard to say precisely what, for any given configuration, what the where these things would lie. Hopefully, if I describe kind of what's the phenomenon behind this, it'll make a lot more sense, and then we'll go from there.
Zico?
Yeah.
I mean, I don't quite get the explanation for why. Maybe I'm giving it.
I haven't given it yet.
Expect things between diagonals.
Why I don't expect things there? I haven't given that yet. No. Yeah.
So there's a reason for that.
There is a reason that, but this one actually won't cover too much. I'm going to go back to the 1D case. This is more of an illustration, but I think it falls out for the exact same reason that I'm going to give the other one. All right, so before I do that, I want to talk a little bit about diffusion models. This is going to be super basic. I don't want to get into all the things. Questions?
The 2 modes in general, you expect that even in much higher dimensions, or is it because it is in this?
Let's talk about higher dimensions in a little bit. Obviously, when you have images, the hallucinations are not smooth interpolations between these images, right? It's not like you have a fuzzy finger on one hand. What's happening there, and I'll preview this a little bit. What's happening there is that the interpolation is in the latent space of the UNet somewhere. And the question I would have is, is there anything about the phenomenon that translates over to those cases? And I think so. I think there is, and I'll come back to that at the end, because I think these phenomena are not entirely separate. I think there's a connection between them, but I fully agree that entirely understanding this phenomenon in higher dimensional images is harder, much harder to really understand. Yeah.
Do you have any experiments where you're just increasing the sample size, the training sample?
Yes, we do have this.
Because your answer to him
Yeah.
suggests in fact that because if you increase the distance, you see less between the farther ones, right?
Yes, you see less between them if you increase the distance, yes.
Yeah, so what do you mean by distance? It seems like you will have to
Yeah.
sample size.
Yeah.
Versus the
Yeah. What I will say to that is there doesn't appear, so for all sample sizes, and I don't, so admittedly, we have not looked at the rates of fall off for this yet as it falls off with sample size. What I will say is this phenomena persists with very large sample sizes, even for very low dimensional problems, to the point where any reasonable estimator should not make this mistake. I mean, here, right, you have on the orders of tens of thousands of samples here in a 1D problem. I don't think this is some failure mode of the estimator slash generating process, not some notion of statistical uncertainty about the points. Yeah. Okay. Let me talk about diffusion models briefly. So diffusion model basically works by modeling a smooth mixture, which are called PT. That's essentially a mixture between a uniform distribution. Doesn't always have to be zero mean. It can be placed wherever. In fact, we place it, wide enough that it sort of covers the whole space. But it's essentially a mixture between the original data distribution and a noise distribution. And so you sort of mix between these two. Literally just sort of interpolating between one and the other. You shrink down your original dependence on x0 and add some noise. And what these models do, at least under one interpretation, and there's lots of interpretations of how diffusion models work, but under one interpretation, what they're doing is they're approximating the score function at every point along this smooth noise interpolated distribution. The score function is just the gradient of the log of the distribution there. And the way that diffusion models work is we model our distribution Q by essentially approximating the score function using a neural network, right? So we just use it rather than, we don't know the true score function. Arguably, sometimes this is easier to model than the density. And if you have this, you can actually have a process with longitudinal dynamics that draws samples from it. So what diffusion models do is they try to directly model this thing using score matching. That's a sort of a common method that's been known for a while for this. And what they do is then they produce a sequence of estimates from some big time, usually called T big T, to T0. And then T0 is sort of your final estimate of your image. That's my sort of content-free 2-minute explanation of diffusion models, at least in the score distribution and sort of in the score function way of interpreting them. And importantly, I mean, this is actually kind of an aside here. It doesn't really matter, except that we're going to use this later on. In addition to producing kind of this estimate of denoised samples from pure noise at this time to your image at the last time, again, or a data point if you're at a 1D case. They also always produce an estimate of the final state as well. So at every point, when you're producing an image with a diffusion model, you have both an estimate of the current denoised image as well as an estimate of what you think the original image looks like. And then you can map between these two to sort of get a sense of how you, or rather you can use both these two to sort of get a sense of how you progress along your denoising chain. Okay, so that's sort of the basic insight into what's going on here. And now I want to kind of get to the punchline, which is sort of what is happening. And it's actually it's exactly, I think, what was already mentioned here about what's happening to make these things happen. I realize I had this animation wrong, so don't read this yet. But the issue, the reason why diffusion models put this mass in the middle, I mean, for this 1D example, it's very obvious why this is happening. Actually, you can just extract it directly. The problem is that the real score function is discontinuous. So the score function, the real score function looks like this. these aren't great displays here, but for this distribution here, the real score function looks like this, because basically if you take the log of this thing, I mean, this is the log of it. If you take the derivative of this, you'll have 3 decreasing functions that do a extreme jump between modes there. Right, so the real score function, especially as you get to the lower time steps, that's where this is the actual data distribution and not a smooth one, is discontinuous. Neural networks, we all know, are very bad at representing discontinuous functions. So when you try to so this is the real score function. When you try to estimate the score function using a neural network as trained by a diffusion model, you get this function instead. And so it's just going to be a smooth version of this, right? We're not adding any regularizers here. This is just the nature of gradient descent applied to a neural network. It's going to create a smooth approximation of this thing. And when I run longevin sampling on this function, rather than this one, these peaks aren't high enough. They're not pushing my samples enough toward this point here, or this region here where you want it to be. And so you're going to get points that lie in the intermediate spaces here. And that's all it is. It's nothing actually mysterious in this case. It's very obvious why this is happening once you look into it. We know the analytic form of the true score function. We could sample according to this, sample according to this. When you sample according to this, no matter how many sampling steps you have or how many supports your chain, this is just the wrong score function. And so you're going to get samples that have points in between the modes. Yeah.
So I'm also wondering, like, so even if I were to try to fit, let's say, MLE using iteratives like, with the gradient descent, and I start with a uniform prior, where the draws are coming from like a discrete mixture.
Yep.
You still have very similar things, right? Because you you start with uniform, you're only trying to decrease the.
I see. Okay. So right. So this has to do with the sampling process. So in the so this is not quite true. So if you do the sampling process where you start with uniform noise, run longevin dynamics, but use the true score function, you will not get this effect here because the true score function has enough sort of mass and the correct derivatives to push you correctly into these regions. So I mean, the way longevin dynamics work, right, is you basically you find wherever you are and you take a little step in this gradient direction that pushes you and you add a little bit of noise, right? That's how longevin dynamics work to sort of sample from this thing. So if you use the true score function, you don't have this problem. You have sufficient sort of discontinuities here to push you toward the right spot.
Yeah, but I was referring to what you would learn.
Yes, yeah. Right, yeah.
The artifacts of the function that you would end up learning.
Mm-hmm.
If I just take a very simple setting where, like, say, I have like a mixture of 3 point masks.
Right.
And if I try to learn it using.
I see. So, right.
Like, if I don't have enough samples, like.
I mean, I
will get a smooth interpolation.
I think you're not. I think there's definitely an aspect of that that's correct. But I just want to emphasize we're not learning the density here, and that's actually quite important. We are learning the score function, right? So learning density is very hard, and even if you have a density you've learned, sampling from it is hard, right? So this is why people don't use density estimation for the most part. In these networks, they've settled on a huge variety of alternative models that don't require density estimation, basically, right? So we've kind of racked our brains to think of alternative things we could do that are not density estimation in all generative modeling for images and stuff like that. For images here, not autoregressive, you could argue that's just density estimation. But we're not estimating the density, we're estimating the score function. The reason why we do that is you can draw samples from the score function and have a nice estimator for that without having to sort of model the density at all.
Yeah,
Even the unnormalized density. Okay.
Like, actually how to estimate density and trying to think of like starting from a uniform noise to learning. Could be learning any functional, but I can.
Okay. Yeah. Maybe we'll talk offline. Yes.
So you're, identifying that neural networks can't represent discontinuous functions that can estimate the score function. That's why this is happening. That suggests that at least in this simple example, just as a thought experiment, some other estimator of the score function that committed discontinuities, but kept the longevin steps what they are.
Yeah.
Have you guys tried that?
So I mean, we've tried just using the real score function, and that obviously works. We haven't thought of other estimators. We're trying to sort of glean insight into what happens when you do use neural networks for this. I think, and we haven't done this yet, to be clear, I think what would be more interesting would be to think about modifying the sampling procedure in a way that accounts for the inherent smoothing of this score function to sort of overcorrect for it. I think that would be the right, because I mean, it's not bad here. I mean, yes, you have a little bit of sort of an attractive point there, but you'll get out of it with noise too. I think potentially, again, haven't done it yet. We'll talk about what we do in a second, sort of to account for this. The thing we have done, well, we'll talk about what we do in a second, but I think a more interesting thing maybe would be to see if we can modify the sampling process in a way that overcorrects for the inherent smoothing of these functions to account for that sort of inaccuracy. That in my mind might be a more fruitful direction, but we haven't gone that route yet at all.
I'm also curious about because if there are like smaller modes, wouldn't that then remove them away?
So yeah, there are problems of, I mean, people call them, mode collapse and stuff like that. So when you have very small amounts, modes with very small amounts of data, to be honest, people do worry about this happening, but what we see is this is actually not the problem in practice for a lot of diffusion models. The problem is exactly that you are over-representing points that are between modes. So in some sense, it's very apparent why this is happening. And by the way, in the 2D case, what you get is just the landscape of that neural network tends to be such that you get connectivity in the path between two modes that are nearby and not between diagonal modes. And for there, I would just throw up my hands and say, this is just a function of the nature of how neural networks end up approximating the data. It's not due to the rotational invariance or like that. If you rotate these points, you get the same connection only to the nearby modes. So I would say I'm not going to give you a great answer to that. I don't think it's going to be super satisfying, other than just to say these discontinuities here happen more between neighboring nodes, or sorry, this smoothing here happens more between neighboring modes in the 2D case than it does between diagonally adjacent nodes.
So for that, you could apply it at one point and then see whether then diagonal point will be the nearest, right?
Yeah, so we've done a bunch of things that are sort of similar to that, where we jiggle them around a bit, stuff like that. Maybe we can. It doesn't look like it's a big jump. There's no sharp jump in it. It just, yes, when you move it connects to its nearest neighbors a little bit less, and then eventually it falls off when it's the distance of the diagonal. I don't think it's anything that deep, to be honest. I think it's just sort of these, this. Oops, what did I do there? This function just happens to. When you fit a network to the score function here, it happens to sort of smooth more in these gaps than in this gap. Yeah.
Isn't this 2D example is just a product of two of just the 1D example?
Yes, but again, there's nothing inherent about the. Oops, that's weird. I have text behind it now. This text, that's strange. If I take this exact same example, I didn't put it in my slides here. If I take this exact same example and just rotate it like this, so now it's not at least independent variables anymore. You get the exact same thing as this, just rotated.
This, let's say, compression-wise, the best way to express your data is the two-dimensional.
Yeah, I mean, so you could argue that this is in fact a product distribution, but you can make variants that are not symmetric in this way, and they still will have sort of, it will still interpolate between nearest modes if you kind of jiggle this a little bit and stuff like that, but I don't want to go too deep into that, because there may be effects that we haven't seen that we're sort of not, I don't really know about, but it's not, I don't think it's sort of a notion of sort of these are only true of product distributions, for example.
Were you also using an MLP here?
Yes, this is our MLPs.
So it's very likely it's not doing the one-dimensional product thing at this MLP.
Yeah. Okay. All right, but there is one thing. There is some sort of a saving grace here, and this is what I mean by the fact that diffusion models know when they're hallucinating. Because if you look at not just the final sample, but if you look at the trajectory of samples that created your diffusion sort of set for any given generation, something very interesting happens, right? Because if you are kind of stuck in one of these over-smoothed regions, what you will tend to do And if you end up wind up more in this space than everywhere else, what you will tend to do basically is you will tend to bounce around more than if you get kind of in one of these modes and stay there. You tend to basically, your sampling trajectory of your diffusion process has much higher variance. And just to sort of drive that home, I'm going to show this plot here. So here I'm showing a few, I think for I forget if this actually ends at 40, but we're zooming in on time 40 here. It might be 100 or so, at looking at a few samples between modes 1 and 2. And we're looking at, so this is kind of, think of as more random samples here, and they are eventually going through the diffusion process to converge to one of these modes. And we look at a few samples that sort of wind up somewhere in the support. I mean, again, I'm being informal here, in the region of reasonable probability mass versus out of the support. And what you see is, because essentially the way to make these, the place where these functions are very similar is exactly in this region here. So if you move if you move your samples to this region here, then the chain of sort of your diffusion chain will much more accurately follow, on the neural network approximation, will much more accurately follow the true diffusion chains you get if you have the real score function. It's really if you are in this region here where these things differ a lot, and in that region, because you are not pushing yourself enough to these points here, your variance is going to be much higher of your chains. And so what you see basically is that the points that end up here wind up undergoing a whole lot more sort of bouncing around in their it's actually it ends up being their estimate of the final point, not just the estimate of the thing. But this is essentially, there's a one-to-one mapping between these two, so it's not hard to compute, not hard to translate between these two. You get much more, much higher variance in your entire sample trajectory. Right? Yeah.
When you train a model with data that looks more like what the hallucinations are doing,
Yeah.
do you still get this phenomena if you, or wouldn't it?
That's a good question, actually. I suspect not, because I think in that case, basically these, so it's a good question, actually. Let me think about that. It's something we should actually we should run. I think it would not be as prevalent there. But let me think about why I believe that. Maybe I'm more biased just to believe there should be different modes in data, and therefore things in between the modes tend to be hallucinations. And so that's my inherent bias that I'm bringing. That's a good question. Yeah. Okay, but if you're not in that case, if the data is actually not connected between modes, if it is multimodal, in the sense of modes of data, now you can't say multimodal in AI anymore, and people think you mean text and speech and images. So this leads to a very simple metric we have for assessing how likely, in some sense, a point is to be hallucinated. And the idea is you just take this trajectory of all your predicted points, and let's look at this variance over the entire sampling trajectory. And if we do this, what we find is we get actually quite good separation between what we're referring to, again, with some threshold here between in support and hallucination. We get very good separation between the hallucinated points here, then their value of this metric, and the value of the metric for non-hallucinated points. So almost all of the non-hallucinated points just do have very low variance in this trajectory, sampling trajectory, and almost a lot of the hallucinated points have relatively high value of the metric. It's of course not. I want to be very clear. It's not a perfect separator here, but it's pretty good when it comes to sort of understanding. There's definitely a difference in these two distributions here. Yeah.
The way you described the figures, if you go back a couple.
Yeah. To which one? This one. Oops. Sorry. Somehow I pressed. There's like a middle button. This is. No. It's. I'm not used to this thing. It does very odd. Yeah. Okay. There we go. This one.
Yeah. I mean, it feels like just naively. Some of these look like they've converged.
Yeah. Okay. So this is a great point. I want to make one point clear. So this is the trajectories of the predicted x0s. And so the predicted x0, you basically, to predict the x0, you take your current iterate and you subtract off the score function actually with a certain fraction of it. And so importantly here, this is not the trajectory of the actual noisy sample. That will bounce around much more. This is the trajectory of the predicted x0, the denoise version. So what's definitely true is the samples that are non-hallucinated, they kind of know where they're going to end up a lot earlier, and that is much more stable. Yes, but that's an important distinction there, which I maybe didn't emphasize enough. This is predicted x0. This is this one here, not xt to x0. Yeah, very, very important there. Because the other samples, I mean, there is, again, a one-to-one mapping, but those will always be noisier, and so you have much more just inherent variance of those things than you have in the predicted x0. Okay, and it's pretty good at differentiating these things. So again, though, with data like this, it's very unclear if this has any real significance when it comes to real data. I think it's a fair critique of this whole agenda we're talking about here. Because we know if you look at 2D data and these models, I mean, no one applies them to 1D data, right? This is not arguably that interesting. But then maybe more fundamentally, is this just an effect of non-Lipschitz, or the high Lipschitz value of neural networks on this one type of score function, which has no real bearing on what it means to really generate images with diffusion models? It's a totally fair possible objection. And to be fair, I don't think this effect is the only thing causing what I'm referring to broadly as hallucinations in real data. I think there are many effects that might cause that. But the point I want to argue now is that I think this kind of analysis is at least somewhat useful in trying to understand the hallucinations we actually see in real data. And I'm going to do this in two ways. So the first thing I want to look at is for the simple shapes data. Are these metrics that we see, are they still useful at differentiating between hallucinations and non-hallucinations? And the answer is very much yes. If we just analyze generated images, look at those sets that have that are hallucinations, right? That are not hallucinations, that are valid samples from this distribution, i.e. they have only at most one shape, and look at that. That's going to be the blue, and we plot this metric that we have here. So the variance of the predictions along our sampling trajectory. We get this distribution in blue. If we look at only hallucinated samples, we get this one in orange. Now, one thing is really important. I'm not yet claiming this is a great way of actually filtering data entirely, because we're inflating the size here to the same. So these are all far less. These are all scrunched down to in this region here. But it actually is not still horrible as a differentiator. The other thing I want to make clear is that this is not sort of a notion of the actual spread of the density. This is sort of this is a histogram of our metric. So you get plenty of data diversity, even if you were to threshold here. There's plenty of diversity in these samples still. It's just that some took a little bit longer to converge, some are a little bit less to converge. There's of course some variance in our metric itself, but it's it's very clearly different, these two classes. Yeah.
How does it compare to just the log likelihood if you use that as a metric to detect?
I mean, so first of all, it's actually very hard to compute the likelihood compute likelihood.
PFOD, right?
Yeah, it's somewhat of a pain. We did a little bit of this, and this is quite a bit better. So if you look at just likelihoods as your thing, there is still some separation, but it's not even close to being this good. We do have that plot in the paper too, I think, or we've done it if it's not in the paper. So maybe you should put it in the paper. But yeah, it is. To answer your question, maybe I should be more direct. It is very different. It is much better, this thing, than likelihood, at least with the estimator's likelihood that we are using, based upon the ODEs and stuff like this. Yeah. Yeah. Because you have to, it's a pain to estimate likelihoods actually with these things. Yeah.
In this case, since we know what is the ground truth,
yes,
anything out of support or out of the training data is not hallucination, right? So we want some of those blue guys there, because they are actually what generalizing beyond the training data?
This is a great question. Are these actually generalizations, and the most interesting generalizations? I could probably do this a bit more, but what I will say is, it does not appear, these samples here do not appear characteristically different than these ones here. They are both just samples. These ones just happened to take a little bit longer to get where they were going in the sampling trajectory. These seem very much just one sample. I can't visually tell between these ones here and these ones here. So I don't think it's like these are the most interesting samples we have. I think it's just there's some variance in this. Yeah.
For your model, is the training loss goes to 0 or near 0?
Let's see. So I wouldn't think.
Like if it over.
I mean, to be clear, the loss here is the score matching estimators, right? So I forget if those go. I don't think those go to 0.
Like if it goes to 0, then would the hallucination just disappear?
I mean, I think it's the nature of score function estimators, and when you use neural networks to not go to 0, that's they can't go to 0 actually. I don't know if they were somehow driven to 0, would you just put the entire probability mass on the training data? Would be my thought, maybe. But I think even then, as I remember this, I know in practice they don't go to 0 in practice. I also think that there likely are failure modes where you can have very low loss while effectively just memorizing all your data. That gives you very low loss on whatever metric you want, on whatever sort of loss, whatever estimator you have. But that doesn't happen in practice because the functions can't represent that very well because those are very non-smooth score functions, and so you don't get that in practice. Yeah. See that?
Do you have a reasonable heuristic for balancing whatever type 1 and type 2 errors? So say
Yeah. So to be honest, we're not using this right now as an actual classifier or filter. I will talk about being filters, but what I would say is the thing I would advocate for is it's not like we actually want all of these. We get sufficient diversity here. So if you're looking to, for some reason, filter your data, I would take basically a pretty aggressive filter and do it that way, because these errors aren't you don't lose a lot by cutting out this part of the distribution. Yeah.
Is that complete for images and other high dimensional distributions as well? That
Yeah.
even things just take longer to convert. They're not more interesting than
Again, maybe I didn't see sort of a more interesting character, at least in these examples here, to these. And to be clear, there are cases where this is actually still not quite as separate. You'll see one in a second, but it was not like these were, again, the most interesting samples. I couldn't differentiate them. Yeah.
But suppose I just ran it with the true score, then you just throw out some fraction of the distribution, and you're saying that's okay.
Yeah, I think that's fine. Yeah. I mean, we can see. We haven't done. So I guess we haven't done this case where is there some horrible bias if you do cut out these things with a tree score function. We should probably look at that. Yeah. Yeah.
Groups more.
Right. So no, it won't. This will not change that either. These things are due to the shape. I mean, these things are sort of true even in the limit of effectively continuous time denoising, and so they do not appear to be a function of sort of the number of steps. Yeah.
Variance over the steps in the diffusion process, right?
Yes.
At each step, I look at the predicted value that I'm achieving, and I take the variance. Over
Yes.
that. At each step, you're running a neural network denoiser.
Yes.
Is it interesting to look at the intermediate behavior versus the objective achieved by the neural network denoiser? Information about how fast.
Yeah. So typically speaking, I mean, there's usually not a good loss function at intermediate denoiser steps, because again, the goal is not to denoise. I mean, denoising is not the goal, right? The goal is sampling from this sort of thing. And I mean, the way these work, right? The way you get like your final state is you basically take whatever state you're in, you predict the final state of it. That's the denoiser part of it, and you see where that kind of lies. And to a certain extent, I don't quite know what the loss. Do you mean the difference between this point and the denoised point? Is that your loss you're talking about, or what loss do you mean? Like,
I mean, presumably every intermediate iteration,
you're trying to denoise your noisy image, right? But then what's the, you don't know the ground truth. It's just drawing a sample, right? It's drawing a sample. So what should be the ground truth about what the denoiser should be doing?
Can I ask what the predicted image would be, or whatever this is, like at an intermediate duration?
That's actually what this is. So this is actually the predicted.
That's an intermediate time step. But I'm saying that the neural network denoiser is running iterations per time step, right?
Oh no, it's just the UNet is a single step denoiser. I mean, yeah. I mean, single multi-layer denoiser, but it's intermediate steps are not interesting there. Okay, so this metric appears to at least be reasonable. Again, maybe not as a discriminator, because there's going to be lots of errors, but as a filter, possibly. But there's one more plot I also want to show, which I think is very interesting. And before I put it up, I'm going to give all the normal caveats about dimensionality reduction and this kind of stuff. Yeah, I know people hate looking at t-SNE plots, but I'm going to show you a t-SNE plot. And I know all the problems about t-SNE and things like this, but I still think it's really interesting. So what we also did is we looked in generated images at a particular type of error. This is the error where you sort of have two squares in the middle region that are generated here. And we look now at the two-dimensional embedding of the innermost layer of the UNet during the generation of these examples. Right, so UNets have, there's an hourglass-shaped kind of network. You run t-SNE on the intermediate element, or the middle element of the UNet. And you get this. And what I'm showing here is I'm showing the t-SNE embedding, a 2D t-SNE embedding of the entire set of many different generations here. The blue ones are all generations that end up having one square in them, and the orange ones are the ones that end up having two squares in them. And what you see is this sort of very nice pattern. I mean, to be clear, this is not perfect anymore because there are sort of points about that also have two squares in them. But for the most part, what's happening here is this region here is region 1. So this is the region, this one here, corresponding to squares at the bottom. As you move around this manifold, you move the square up in the space. I don't want to put too much emphasis on sort of interpretability of latent states in networks, but for simple problems, you can find them, and this is one we found. Right? And now, one thing that's very interesting is that if we think about this mode interpolation phenomenon, one thing we found is that there's very definitely some points in this region here, all of which have two squares. So this is not like elsewhere where there's sort of a mixture of both of these. All of these points have two squares in them. And they're all two squares that are sort of on the top and the bottom. And there's none that only have one square in this region. So I would argue that at least this hints at the fact that you do, in fact, see this kind of mode interpolation phenomenon happening in the latent space of these networks. Maybe not unsurprisingly, because again, you're applying networks to these latent spaces. They are Lipschitz continuous more than the true function maybe should be. And this is where you're seeing a lot of the hallucinations from. So I think that's at least an interesting data point at highlighting, what might be going on in some of these hallucinations. Last thing I'll say is this also, to a lesser extent, I admit, these ones are more overlapping, I admit. So we're getting less and less discriminative as we go along. But we see a difference also. So we generated a bunch of hands, and we just counted the number of fingers on the hands. Here we had to do it manually, so there's fewer examples here. The rest we could do automatically. This one we had to just count. Again, for hands with more samples, hands with more fingers, you tend to get higher levels of our metric. We couldn't quite find the same pattern in t-SNE. I just think that this is sort of a very nice thing because you can kind of look at only a very narrow region of certain types of hallucinations. We couldn't do that with hands, but I suspect something similar is likely happening in the latent space there too. All right. Before I end, and I'm, as expected, only got through the first portion. That's fine. This is the more interesting portion anyway. I want to mention a few things, a few sort of implications of this to other things. So there's a lot of discussion these days about iterative recursive modeling. So if I train a model on generated data, what happens? And bad things happen, right? So the internet was forever poisons now after ChatGPT. Only generated data from now on is ever going to exist in the internet, and so we're all going to have a hard time training our next models. And we do see that, in fact. So if you take this process and iteratively generate, iteratively throw out your data, train a new model and generate data, and repeat this process, as you would expect, because you see this sort of smearing of the modes, you eventually get just a mass of barely recognizable density of your points there. However, because we now have a metric by which we can filter our data, if we do the same thing, I'm actually just showing the sort of the plots here. If we do the same thing, and only as we generate data, filter it, you actually get both. And I should probably put a figure up, but I think we have some of them again in the paper. You both keep your number of hallucinations lower over time, not gone entirely, but you keep it lower over time, while still retaining reasonable fidelity to the distribution. And so we do it for MNIST too, and for MNIST you also can have a lower FID, which is some sort of notion of how close you are to the real data. Right, so at least I think this doesn't, to be clear, this doesn't solve the problem of data pollution with synthetic data, because it requires you to actually do this when you're generating samples before you put them online. But at least it hints at a way in which we could start to filter data that will not be as bad for future generations of models that we train on this data. All right, so I think I'm actually going to end here. So let me just end here, and then we can break for lunch. I don't want to stop people's lunch. Okay, but you still can stop people's lunch. Yes.
Doesn't that last picture you showed sort of contradict that neural nets have difficulty with discontinuous things? Because at some point those scores are getting pretty smooth, right? So like at generation 10, the score should be pretty smooth already. It doesn't have discontinuity. So
yeah.
It
is over-smoothing it, yes.
It was non-smooth to begin with. It's just that you're over-smoothing.
Yeah, so I think at every iteration, you get a smoother version of the true score function. Because no matter what, I mean, so when there's a discontinuity, it's particularly obvious, right? But no matter what you do, if you fit a function to it, you will tend to bias yourself towards over-smoothing it, yeah. Plus, there are regions here that are kind of discontinuous too, because in the middle there would be those things still. But yes, yeah, you continually over smooth. Yeah. I guess I'll just also say, so maybe to have one takeaway of this, right? Hands with lots of fingers aren't necessarily something that diffusion models believe. Just because they generate something does not mean they believe it. Again, hugely anthropomorphizing these models. Some of these artifacts could just be the fact that we are between two different images that we do believe. And so hallucinations are not just a function of the model and the data and all that kind of stuff. They can also be a function of the sampling process. And we should be, I think there's lots of interesting kind of work to be done. I've actually had some other final thoughts. Let me just put those up. These problems, these are highly visible problems in AI systems, right? These are sort of what everyone talks about when, oh, there's hallucinations in AI models. And they're typically not studied that much, I would argue. Maybe I'm overgeneralizing here, of course, but I think they're often not studied that much in ML theory and stats due to what's perceived as the rather ad hoc nature of these things. And they are exceedingly ad hoc, and I fully admit that. But I think there's tons of potential connections and points of common interest. And if there's one sort of possible takeaway from this, it'd be the hope that I can get people to start thinking about these phenomena more and think there may be very simple problems about just simple estimation errors that can lead to these very well publicized, very prominent, problematic downstream effects in AI models. So thanks very much.
In the interest for time, if there's like one quick question and then we break. Yeah.
So your comment about how they believe, I mean, It's hard to.
Yeah.
Just thinking, if you think of the thing they believe is the score function that they've learned, they do believe that the score function is smoother than it should be. So
Yeah.
we know that we can't trust them
Sure.
when it comes to smoothness.
That's true. I guess I wouldn't want to. Yeah, you're right. So the question when I say believe, I more mean, is there a internal differentiator in these models between points that are hallucinated in some simple way and points that are not? That's and so yes, put in a less controversial anthropomorphized sense. This is sort of what I mean. Yeah.
All right, thanks, Zico, again.
So I just had a couple of questions.